Okay, so I'm going to spend a couple of minutes going through with some of the position time graph and velocity time graph stuff that people have been asking me about. I'm going to start with some of the basics, and then we'll move into some of the more complicated stuff like calculating accelerations and what acceleration graphs look like on a velocity graph. The first thing I need to point out is that I don't have a marker, so I'm going to go get one. Okay, a horizontal line on a position time graph. We have always said that that means that you are standing still. Now that is accurate, but that is not the most accurate way to think of it. Okay, standing still is the common sense way to describe what you're doing, but what is actually happening is your position is not changing. Okay, now yes, that means you're standing still, but that particular phrasing, a horizontal line, means that the value is not changing. So on a position time graph, a horizontal line means your position is not changing. On a velocity time graph, a horizontal line means the same thing. Your velocity is not changing. And on an acceleration graph, it would mean your acceleration graph or your acceleration is not changing. When we talk about a sloped line, it means that it is changing, and we start talking about are you a positive change or a negative change? So this rather crooked line would be a positive change in your position, while this one would be a negative change in your position. Now, whenever you have a sloped line, then you can calculate the slope to go up a step in the kinematic universe. So I'm going to pause this for a sec. Okay, so I showed this information to some of you the other day. This is mainly just some equation information that's going to be helpful, which you will get this on your velocity time quiz, which is posting today. This information will be available to you. Remind me to pass that out before you leave. But this is the stuff that I want to focus on. So in the hierarchy of kinematics, the top of this is the simplest information. The bottom of this is the most complicated information. So position, which we use displacement to report, is going to be the simplest thing that you can get. The derivative of position is velocity. The derivative of velocity is acceleration. Derivative of acceleration is jitter. The derivative of jitter is jerk. Now what that means is the change in. So everything is the result of a change in the thing above it. So you get a jerk when the jitter changes. You get acceleration when your velocity is changing. The simplest definition of acceleration is a change in velocity, which is the 3-word definition I was going for the other day. Change in velocity. You can use that for any of these. Velocity is a change in position, or a change in... position is probably the best way to put it. Change in the position. Okay? Jitter is a change in the acceleration. Acceleration is a change in the velocity. Okay? And there are trends that when you have that list written out, that you can get. So let's say that right here is velocity. If we want to determine the thing above velocity, or the simpler item, we would use the area under the curve to calculate it. Okay? If we are trying to determine the next most complicated thing, the thing below it, we would calculate the slope. Okay, so if we have a horizontal line, the slope is 0, then the velocity is constant. If we have a horizontal line on a position time graph, it means the velocity is 0. But if it's actually sloped, then we can calculate the velocity by calculating the slope. So if your line is sloped, it tells you that whatever is right below that is non-zero. So on a jitter time graph, a sloped line would indicate the presence of a jerk, or a non-zero jerk. On a sloped position graph, it indicates the presence of a velocity, a non-zero velocity. Does that make more sense then? Okay. Now, this one we're never actually going to calculate, but if you are looking at a velocity time graph and it's not a slope, it's a curve, it indicates a non-zero jitter because it is 2 below. So that's why there's 2 arrows here and only 1 here. So if we start at velocity and we go down 2, that is non-zero in order for this graph to be a curve. Which should make sense if you think about it, because if you think back to our position graphs, when we had acceleration, a change in the velocity, our graphs curved. It's for the same reason, because the 1, 2 down was non-zero. You were accelerating as you walked in order to get that curve. Okay, now I'm going to switch to velocity, because velocity is a little more complicated because of the negative values you can actually get on all the rest of these except for position. So I'll swap that up real quick. All right, first big difference in our velocity graph and any subsequent graph that we might take from this list is the presence of a negative side. So the bottom of our graph is no longer at 0. The middle of the graph is 0. All of these are going to have just as much negative possibilities as they do positive possibilities, which breaks your brain if you're not used to thinking about it. So, the way you determine direction on a position time graph is the positive or negative slope. So if it has, and I'm pointing the wrong way, so I'm going to move over here to do this. So if you have a positive slope on a position time graph, then you have a positive velocity. If you have a negative slope, then you have a negative velocity. But it's way easier on a velocity time graph to determine your direction. Positive velocity is away, negative velocity is toward. So if your velocity is positive, that means it's above the 0 line, then you're moving away, regardless of what your slope is. You are moving away from the detector if you are up here. And if it's down here, you're moving toward the detector. No matter how far away it is, the direction is indicated by either positive or negative. I don't care what the slope is. I don't care how horizontal it might be. Up here positive, away. Down here negative, toward. Same goes for acceleration, jitter, and jerk. Positive indicates you're accelerating away. Negative indicates you're accelerating toward. Now, horizontal line, we have a horizontal positive velocity and a horizontal negative velocity. So this person is traveling at a constant speed away from the detector. This person is traveling at a constant speed toward the detector. But both are traveling at the same magnitude. The only difference is the direction. This one's going negative, so toward. This one's positive, so away. Now, when we talk about sloped lines, slope indicates that we're going down 1. So this is a velocity graph, so we have acceleration. To determine the acceleration, we just calculate the slope of this line. So if we want to determine what the acceleration is of this person as they made this line, then we just do our slope, which is going to be final minus initial y over final minus initial x. So, I'm going to pause. So I'll go through this once with the video, and then from here on, I'll pause it every time. So our initial position, that's the wrong word. Our initial velocity is 0. I'm standing off screen, but my hand isn't. Okay, our initial velocity is going to be 0. So that's the y-axis. So 2 minus 1 is going to be minus 0. Final is over here, and that's supposed to be 1.5. So I'm just going to use 1.5. By the way, whenever I give you a graph like this, the endpoints or points of significance will always be at one of the labeled axes markers, because I don't want you trying to guesstimate where something is. A good trick is to try and use a note card on the computer and line it up with your y-axis or your x-axis, whatever you're trying to mark, and it will make it easier to tell where you're looking at. Obviously, this note card won't work for this graph because this graph is enormous. So now our x. The x-axis on this graph we take from here. So our final is going to be time, is going to be 2.4. So x2, or x final, is 2.4, minus the initial, which was 0. We started moving at 0. Now in this case, the minus zeros just go away. And so we get 1.5 divided by 2.4, which is 0.625. Now, I will always put a 0 here because my decimal points are sometimes hard to see. So now, is this positive or negative? I don't know why I started talking to the class, but yeah. Since this is positive, it indicates that our acceleration is positive. If the acceleration is positive, then our acceleration is away from the detector. On this one, when we do it, so if we use the same calculation with our final point and our initial point here, then we end up getting negative 0.625 as our acceleration for this one. Now, this time we have a negative, so our acceleration is against the velocity. Now, this is something I want to point out that's very important. When you're talking about velocity and acceleration, and for any other pair, when they are in the same direction, then the lower is going to be increasing. When they are in opposing directions, the lower is going to be decreasing. I'm going to use acceleration and velocity to explain what I mean. Here, acceleration and velocity are both positive. What's happening to our velocity as we go is it's increasing. So we are speeding up as we move through here. Over here, our acceleration is negative, but our velocity is still positive because we are still above 0 on the velocity graph. So here, our velocity and our acceleration are in opposing directions, and so we are slowing down. What happens then when you cross this line? Think about it for a second. Okay, hopefully we answered that while it was paused. When you cross this line, up here, you are moving away. Down here, you are moving toward. So when you cross the 0 line, you turn around. You change your direction, so you're now going in the opposite direction of where you were before. If you cross it going this way, you've gone from moving away to moving towards. If you cross it going this way, you've gone from moving toward to moving away. Acceleration and velocity. The directions determine whether you're speeding up or slowing down. So, let's say, I'm going to pause this and draw this. All right, I have sketched this little pea plant-esque thing up here because I keep Punnett square. I have up here to kind of show you what happens based on whether your velocity and acceleration match up or not. I write big, so I'm going to use arrows instead of actually writing out speeding up and slowing down. So let's start with the velocity away. So a positive velocity If your acceleration is also positive, indicating your acceleration is away from the detector, your velocity and your acceleration are in the same direction. And that's going to cause you to speed up. But if you are moving away and your acceleration is toward, your acceleration is fighting you while you're trying to move. And it's going to cause you to slow down. And then here's the one that breaks people's brains. Now we're moving towards the detector because all negative means is the direction. It just tells us the direction of the velocity. So negative velocity, positive acceleration, same thing. You're trying to go this way, but acceleration is pulling you back the other direction. And so you are slowing down. But when both are negative, they're both going in the same direction, you end up speeding up again. So many people tell me that because they're both negative, you have to slow down or stop. That is not the case. When the signs agree, you speed up. When the signs oppose each other, you slow down. Okay? So, I'm going to pose this to everybody in the video, everybody watching the video, and to the 4 people who are watching me record it. Which of these two is speeding up? All right, so if we call this graph E, or this line, not this graph, this line E, and this line F, F is speeding up. E is slowing down. There are 2 ways you can tell that. One, this has a positive slope and a negative velocity. So it has a positive acceleration and a negative velocity. So they're going in opposite directions, which means this has to be slowing down. While this one has a negative slope, so a negative acceleration, and a negative velocity, so it has to be increasing. Or you can also tell because this one is becoming closer and closer to 0, and this one is moving farther and farther away from 0. So there are 2 ways to determine that information from this graph. The last thing that I want to talk about is calculating position, not position, calculating displacement from a velocity time graph. And I need to make some changes before I can do that. All right, I have made a couple changes to the graph so that I can actually show you what I want to show you. First, we are going to determine the displacement of this person, the person who made this line. Okay, if we are determining the displacement from a velocity time graph, we are going up 1. So we are going to use the area under the curve. Clarification. Area under the curve means the area between the graphed line and the 0 line. So we are not measuring from here all the way down to the bottom of the graph. We are measuring from here down to the 0 line. So if we ignore this little piece here, which is super inconvenient, but I need anyway, this is basically just a rectangle. It is 1.5 meters per second tall. And it is 5 seconds long. So to calculate the area of a rectangle, we take the length times the width. So 5 seconds times 1.5 meters per second. We take 5 seconds times 1.5 meters per second. Our seconds cancel because this one's in the numerator and this one's in the denominator. So we get 5 times 1.5, which is going to be 2.25? Question mark? Or 22.5. Okay. All right, I can't math. This is 7.5, and that would be 7.5 meters. So that would be the displacement for the person creating this line. Now that's for a simple straight motion where the velocity is not changing. For this bottom line, our velocity is constantly changing. So to calculate this, we do the same thing, but we have to break it up into smaller pieces. So, for example, if we were going to calculate AB, the area under the curve would be not this, but between the graph line and 0. So we want the area of this section. Unfortunately, that's not a real nice, convenient shape, so what we're going to do is break it up into two sections where we have a rectangle and a triangle. So we can calculate the area of these two separately. Okay, I want you to calculate real quick the area of AB, BC, and CD. Pause the video to do it to make sure, and I will put the answer up here in a second. So you have to pause it. Okay, so before I cut you loose on the others, I want to show and explain the first one. So it is negative 0.5 meters tall because we are below 0. So the height is negative 0.5 times 1 second wide would give us, I mean, anything times 1 is itself. So negative 0.5 here. Then we add to that the area of the triangle, which is negative 1.5 tall, because we take the negative 2 minus negative 0.5. 2 minuses you add, so we get negative 1.5. Still 1 second long, and then since this is a triangle, we divide by 2. So we've got negative 0.5 plus negative 7.5, which gives us negative 8 meters. So if you got that one wrong, you might want to go back and check the other two before you look at the rest of this. Okay, so this one being just a rectangle, the same as this rectangle, comes out to just negative 0.5 meters. This one is just the inverse of this, so same rectangle, negative 0.5. And the area here is still, of the triangle, is going to be negative 7.5, so it's also negative 8. Now, the next one I want you guys to do is I want you to take a crack at DE. I want you to figure out the displacement from D to E. You're going to have to calculate it as two separate triangles instead of a triangle and a rectangle this time. Okay, so when you do the math for this triangle, it's about 0.6 to the point where it crosses 0. So the triangle is going to be 0.6 wide, 0.6 seconds wide, and negative 2 meters per second tall. So multiply those. We have to divide by 2 because it's a triangle, so we get negative 0.6 for the total area here. On this one, we go from 0.6 to 4, so it's 0.4 times only 1 meter per second tall. So 0.4 times 1 divided by 2 comes out to positive 0.2. So here's the big stick that you have to remember here. Since it crossed this line, we changed our direction. Since we changed our direction, we have to subtract these two numbers, because this one is positive and this one is negative. Here, they were both negative, so we could add them up. But here, one's positive, the other's negative. We have to subtract them. So 0.6 plus positive 0.2, or 0.2 minus 0.6 gives us negative 0.4 meters. Is the total displacement from here to here. Okay, and then the last one would just be the area of this, so I'll go through that one more time real quick. It's 1 second wide times 1 meter per second tall So it's 1 meter. Okay, that's where I'm going to wrap up that video. I'm going to make another video here in a second because this one's getting kind of long and talk through what each graph would look like describing different motions and see if I can't help clarify some of the issues there. So that's it for this video. I will post the second one about the same time I post the first one. So I'll be right back.